Hello, welcome back. We're working on the 8th lesson now, Module 8. So we talked a bit about the Earth, and let's talk a little bit more. So here on the Earth, we're talking about the atmosphere of the Earth. As one increases in altitude in the Earth, the air pressure goes down. But some weird things happen with the temperature. And here, we live in the troposphere. This is where we live. And as we increase in height in the atmosphere, in the troposphere, the temperature goes down. That means at sea level, at Hilo, as one goes up in the Big Island up to Mauna Kea, the temperature gets down, gets colder the further you go up. Then one gets to the stratosphere where the opposite things happens. Stratosphere is one increases in altitude, the temperature goes up. So it's the opposite. Mesosphere is similar to the troposphere, whereas increase in height means colder temperatures, and thermosphere, higher altitude means warmer temperatures. Then beyond the thermosphere is the exosphere. That's also known as outer space. So where is everything? All the mountains, all life, we're in the troposphere. In this picture shows an airplane up in the stratosphere. That's not entirely true. Most airplanes do not go that high. Most of them stay in the troposphere, but they can go, the big jets can go in the stratosphere. Ozone layer is found in the stratosphere. Ozone in the stratosphere is good. Ozone in the troposphere is bad. That's pollution. Ozone is pollution in the troposphere, but it's beneficial up in the stratosphere. Meteors can penetrate into this mesosphere, but some of them go even further down, depends on the size. They usually don't penetrate that far though. And northern lights, also known as aurora borealis, can be found in the thermosphere. What is the atmosphere made of? Well, dry atmosphere, depending on where one is at on Earth, the atmosphere contains a variable amount of water. We have a lot of water here in Hawaii, but other areas, if you're in a desert, will have less, for instance. But the dry air without water is about 78% nitrogen, 21% oxygen, 1% argon. And nitrogen is fairly inert, slightly reactive, not very much. Oxygen is extremely reactive, and that's what we need, that's what we use for breathing. Also, trace amounts of carbon dioxide. Carbon dioxide is relatively important because it's plant food. Also in the stratosphere is the ozone layer, and this helps to give the Earth a UV shield. Particles that have, so there's also solids and liquids. Particles with less than 10 microns are called aerosols, and larger than those are called particulates. And particulates, what are particulates and aerosols? There's a salt aerosol at the beach. Maybe you can smell it, I can smell it. And then if I park my car by the beach and then when I leave, I have this salt layer on my car windshield. What does that come from? It comes from the waves crashing, and after the waves crash, they have little tiny water droplets, and then the water evaporates and forms an aerosol. So there's also dust as another aerosol. Let's talk about atmospheric chemistry. We're going to talk about the nitrogen cycle and the oxygen cycle in particular. And the nitrogen cycle, there's a lot of nitrogen in the atmosphere, which we talked about previously. Where did it come from? It came from volcanic activity. And nitrogen is fairly inert, so it accumulates over time. And then nitrogen can be fixated or reacted with. How do you react it? Lightning bolts can do it. Lightning can break nitrogen bonds. So can bacteria called cyanobacteria, also known as blue-green algae. And industry can do it. Industry can fixate nitrogen fertilizers. And then bacteria can then denitrify the soil and turn it back into nitrogen gas. Now, oxygen, we're talking about the oxygen cycle. The Earth, as far as we know, is the only planet that has a significant amount of oxygen. And that oxygen specifically comes from plant life. Even more so, algae. Algae is a primary source. About 80% of our oxygen comes from algae. And a little bit from terrestrial plants, but mostly algae. And then that algae, we need it, we breathe in, and we use it. It can also oxidize metals, so oxidation of metals. And actually, when the oxygen first appeared on Earth, when algae appeared, oxygen did not accumulate in the atmosphere for about 1 billion years because it was too busy oxidizing metals. And then ozone, when the oxygen gets up to the stratosphere, the ozone layer can form. As long as the sun is shining and there's oxygen in the atmosphere, we are going to have an ozone layer. And ozone depletion is a problem. It was formerly believed to be from CFCs, chlorofluorocarbons. They still produce some ozone depletion. The primary cause of ozone depletion is volcanic eruptions. The volcanic ash and the ice crystals from it. Now, humans don't help, but we're not the primary cause. But the problem is because of these ozone holes can cause a little bit more ultraviolet light to get through. And there's 5 primary pollutants. The EPA talks about 2 more. We'll bring in the next slide. But these are the most of them. Carbon monoxide, volatile organic compounds, nitrogen oxides, sulfur oxides, and particulates. And these can form secondary pollutants, which we'll talk about later. And ozone is listed in the next slide, but it's a secondary pollutant, truthfully. Catalytic converters, though, there's ways to mitigate these pollutants, and carbon monoxide, volatile organic compounds, and nitrogen oxides can be greatly reduced by catalytic converters. And also, particulates can be mitigated. So here are the other sources. I didn't talk about lead. Lead used to be as a fuel additive in gasoline, but we don't use it anymore. Carbon monoxide, where does it come from? It comes from transportation. That's where it comes from. And we have the sulfur oxides, nitrogen oxides, and then those are released and oxidized and then react with water to form sulfuric acid and nitric acid. Of course, nitrogen oxides from automobiles can be mitigated by a catalytic converter. Likewise, sulfur oxides from power plants can be mitigated by wet scrubbers, so it's not they can get rid of them. But some of them escape, and other sources too, like the volcano. Kilauea here releases a bunch of sulfur oxides, and those have caused Hawaii to have terrible acid rain. But as you can see here in Hawaii, we have very lush plant life. So why do we have lush plant life in those terrible acid rain? Plants are used to it. That and acid rain adds nutrients to the soil, but it also acidifies the soil. So the plants have to be used to acidic soil. And if there's an area that does not have acidic soil, then there's acid rain, or more than normal acid rain, then that can damage the plants. It also can damage waterways and whatnot. Now, next slide. Yeah, here is a catalytic converter. Think of a catalytic converter like a honeycomb that has little particles. They look like little soccer balls if you look on them under an atomic microscope. These little soccer balls in a honeycomb, this little tiny zeolite honeycomb, as the nitrogen oxide, carbon monoxide, and hydrocarbons go through, they react and form safer substances coming out. And these are how you get rid of particulate matter. To the left here shows an electrostatic precipitator. Basically, it charges the particles and it sticks to the walls. Then the bag filtration works similar to a vacuum cleaner, where the dirty air comes in and gets trapped in the bag while clean air goes out. Smog, when we talk about smog, usually we mean photochemical smog, but let's talk about industrial smog. This is sulfur dioxide and particulate matter. Also known as London fog. This was really heavy in London during the Industrial Revolution. Also, you might find some of this on the Big Island. Some of the VOG, or volcanic fog from the volcano, this is some of it on the Big Island. Out here in Oahu, I live in Oahu, and some of the other islands, you can get a different type of VOG. Those are sulfate aerosols. So the sulfur dioxide reacts with oxygen to form sulfur trioxide, reacts with water to form sulfuric acid. And that reacts with other things to make other salts, such as ammonia, that occur in the plant life, can form ammonium sulfate. And that is the VOG that I experience out here on Oahu. And photochemical smog, when the normal person says smog, that's what they mean. They mean photochemical smog. It's this brownish haze, and I've seen it in LA. It's not very pretty. And it's from volatile organic compounds, nitrogen dioxide, and sunlight will form photochemical smog, and it's dangerous. And like LA, temperature inversion causes a problem. So here shows a temperature inversion. So to the left shows normal air, where cold air is on top and warm air is on the bottom. Now, maybe you've heard of the phrase before, hot air rises. That's not entirely true. The truth of the matter is cold air sinks. As gases warm up, they expand, and if the gases above it are cold, what happens is gravity pulls the colder air down because it's denser, and it pushes the warm air out of the way. So if there's warm air above cold air, that's a problem because convection won't work, and all the pollution that one generates, one gets stuck with. And certain areas of the country have temperature inversion problems. Los Angeles is one. Another area like Mexico City is another one. And then in those areas, smog can form from sunlight, nitrogen dioxide, and volatile organic compounds. Acid rain we've talked about quite a bit. Besides harm to plant life, it can damage buildings. So calcium carbonate, which is limestone and or marble, and cement, and it can destroy them. So here shows some pictures of a cathedral and a statue that over time acid rain could harm those. Ozone layer, so the majority of ozone layer depletion is from volcanic eruptions. But as long as there, like I said before, as long as the sun is shining and we have oxygen, we're going to get ozone. But the problem is that when we get these periods of ozone depletion, there's going to be more ultraviolet light entering the lower atmosphere. And we're trying to mitigate the small contribution humans do. One of them is to discontinue CFC uses, use hydrochlorofluorocarbons, HCFCs. Problem is that they're more toxic and they don't work as well. So it's a risk versus rewards benefit. Here's the ozone hole over Antarctica. Due to recent volcanic eruptions in Iceland, there's going to be an ozone hole forming in the northern hemisphere as well. That's not going to affect Hawaii at all. It's just going to be Alaska, Canada, and Siberia. And a lot is known about, a lot of people are talking about climate science, and a lot of people are worried about global warming, but not very many people know much about it. So I'm going to talk a little bit about climate science. First of all, people are afraid of the greenhouse effect. That's not true at all. The greenhouse effect is extremely important. Later on, we're going to talk about the moon. And the moon has its negative 150 Celsius at night and 125 Celsius during the day. That's about minus 250 Fahrenheit during the night, 250 Fahrenheit during the day. So the moon is very hot at daytime, very cold at night. But the Earth has an average temperature of about 6 degrees Fahrenheit. And the moon has an average temperature of about 0 Fahrenheit. And, well, what's the difference? Well, the Earth has an atmosphere, for one. And secondly, the greenhouse effect of the atmosphere brings up that temperature quite a bit. And if we didn't have that greenhouse effect, the Earth would be much cooler and life as we know it would not exist. So where does the greenhouse effect come from? Mostly water. Water is the primary greenhouse gas for the Earth. It's a very powerful greenhouse gas. And where does most of the greenhouse effect happen? It happens in clouds. And it seems that cloud cover that's high in the atmosphere warms the Earth, and cloud cover lower in the Earth tends to cool the Earth. But we're still discovering things about this. We don't really entirely understand it. But we do know it's mostly from water. Carbon dioxide, is, people think it's a strong greenhouse gas. It's a pretty weak greenhouse gas, to be quite honest with you. If that was true, the temperature across the globe would be relatively uniform due to latitude. But water, the concentration of water differs, so that's what rises to the different climates that we have on here on Earth. And what is the source of the climate? The sun. The sun is the primary source. And the sun is also unique. It's a very consistent star. Most stars are not as consistent as the sun is. And the sun also goes through cycles about every 11 years. It's really every 22 years, but when one cycle decreases, one increases. And also, maybe you heard the El Nino, La Nina. A warm ocean current causes the El Nino, and a cold ocean current causes the La Nina. And the cold ocean current, the La Nina that we have right now, is why we've been having crazy weather in the continental United States. It's the cooler weather that's causing the crazy weather. And the El Nino, that corresponded to the very warm year 1998. So we've been experiencing cooling recently. It's hard to pin down. We had an El Nino last year, but we still experience cooling. It seems to be the sun is the primary source. And we have two things going on where the greenhouse effect is trying to warm the Earth, and weather in general cools the Earth. And the theory of anthropogenic climate change, also known as global warming, this is a very unique theory because, well, in contemporary science, most things to be accepted science need experiment to back them up. The difference for global warming is that the proof is in climate models and not in real data. But the climate models suggest that carbon dioxide, increasing levels of carbon dioxide, will cause a warmer climate. And the problem with this is that anyone who tells you that more greenhouse gases means a warmer climate is either ignorant or lying to you. The simple proof is, we talked before about water being a powerful greenhouse gas. When water warms up, more water evaporates. So when, if we assume that's true, more greenhouse gases mean warmer climate, then water evaporating oh, so if we say that, well, then water evaporates, will warm the earth, which will cause more water to evaporate, which will warm the earth. This would continue until the oceans boil away. And the oceans have not boiled away, so you know that that's not true. But this theory based off of climate models says that human causes will overcome the natural cooling effects. And if you also look at the theory, the models, it's not carbon dioxide, it's water that does the real warming, not that. And the carbon cycle, let's talk a little about the carbon cycle. The primary source and sink for carbon dioxide in the atmosphere is the ocean. The ocean produces most of it, it also absorbs most of it. And we know that also, we talked about algae is mostly the source of oxygen. It takes carbon dioxide and turns it into oxygen, turns it into glucose and oxygen. And we have other sources too. Terrestrial vegetation produces some oxygen, not very much. And there are other sources, both human and even larger than that, non-human. And let's change topics, talking about the atmosphere. Let's look at the Earth. The nickname for the Earth is the blue planet. So that's our nickname. Why are we called the blue planet? Well, look at it. It's blue. And not only, why is it blue? Well, because water. The Earth is a unique place because of the large amount of liquid water on the surface. As far as we can tell, the only other heavenly body that has a large amount of liquid in the surface is Titan. That's a moon of Saturn. But the Earth is relatively unique by how much liquid we have on our surface. And water is very precious. The Hawaiian word for someone to be rich or wealthy means that he or she has a lot of water. So water is very precious. It's very unique as well. Water is strange, among other things, because one of the most common solids floats in water. Most solids sink in their liquids, but water has a very common form that floats. There are solid forms of water that sink, and in the ocean there is a lot of ice in the bottom of the ocean. And that's a different type of ice. It's not the ice that you see, that you come in contact with normally. So the ice that you have in your water or soft drinks, that's alpha ice, and it floats in water. And also, water is a great solvent, and that makes it really good for transporting nutrients, makes it very good for transporting toxins too. So that's important to us because our blood plasma is mostly water, and that's how we get our nutrients to our cells. But at the same time, our bloodstream can also transport toxins to our cells as well. So where's the Earth's water? Well, surprise, surprise, most of the water on the surface of the Earth is in the oceans. And that's not surprising to find out. Then about 3% of the water, though, is fresh water. And where is that fresh water found? Mostly in the ice caps, specifically Antarctica. Most of it is in Antarctica. And other than that, there's groundwater and surface water. There's quite a bit in groundwater. And the surface water, most of those are found in lakes, but a very small amount are found in rivers. Now, why do we care about rivers? If you're here in Hawaii, not a big deal, but a lot of cities have grown up around rivers. So things like New York City is on the Hudson River, New Orleans is in the Mississippi River. So a lot of cities pop up around rivers. A lot of cities pop up around sources of water in general. So what's in water? Water that has less than 1,000 parts per million, or 0.1% salt, so dissolved solid. What's a dissolved solid? Salt. Salt is a dissolved solid. I'm sorry, that's 0.1%. And the ocean is about 3.5% percent salt. The human body, we are about 0.9% salt, at least that our blood is. So that's why if we drink salt water, it doesn't quench our thirst. And there are other places saltier than the ocean. The Great Salt Lake and the Dead Sea are about 25% salt water. There are places also where water is called brackish. Brackish means that it's not pure water, it's not fresh water, but it's not as salty as the ocean. San Francisco Bay is an example of brackish water. And with the water cycle, the water is being recycled and purified. So here is a United States Geological Survey picture. USGS shows the water cycle. And so a big water source like the ocean, the sun heats up the water, and the water evaporates, and then the water condenses to form clouds. Then precipitation comes down, and then that precipitation goes into rivers and streams, and some of it goes into the groundwater, goes into lakes. Ultimately, it goes back into the ocean, and then repeats the cycle. So what's in water? Well, water has a very high boiling point. So water is 18 grams per mole, and it has a boiling point of 100 degrees Celsius at 1 atmosphere of pressure. That's very strange, but how light water is. Well, what gives it such a high boiling point is the hydrogen bonds. Water also has a very high heat capacity. So what does heat capacity means? It means that it can absorb a lot of heat without a rise in temperature. So metals have a very low heat capacity. So I knew this when I was a kid. I used to like going to the pool, and if I went to the pool and when I came back in the car, if I touched my seatbelt, it would be really hot. If I had a bottle of water in the car though, and the sun was shining in, the bottle of water would be warmer, but it wouldn't be nearly as hot as the seatbelt. But also when I touched the seatbelt, it was hot, but then it got cool really quickly. That's the same thing for water. If you put your hand on a hot spoon, it'll be hot, but then it won't stay hot for very long. It'll kind of cool off. If you put your hand in boiling soup, it's going to really, really hurt because the heat capacity, how much energy water can carry is so high. And this also caused the Earth to stay at a relatively constant temperature. And we compared this with the moon. So here in Hawaii, we have a really constant temperature as well. And we talked about this before, how it's a very powerful greenhouse gas, causing 95% of the Earth's natural greenhouse effect. And here are some other specific heats. And so you can see how water is so high at 4.18 joules per gram Kelvin, whereas over here you look at different metals like iron. Water is almost 10 times as much the heat capacity as iron. So what else about water? Water has a very high heat of fusion and vaporization. So maybe you've noticed this. If you get out of the ocean while you're wet and the wind blows, it gets cold really fast. The reason being is because the water is evaporating. Well, there's another reason too. It's the heat transfer coefficient. So it's not entirely vaporization, but as the water evaporates, it takes a lot of heat with it. And then as water freezes, it releases heat. So the amount of heat that it takes to evaporate water, the same heat is released when water condenses. So maybe you've noticed this. If you go to the gym and you like going into the steam room or the sauna, if you go in the steam room, you get hot really, really fast. The reason being is when that steam condenses on you, it releases that heat of vaporization, and you can get hot really, really fast. And likewise with water freezing, when you put ice cubes into your water or soda to cool it off, as the ice melts, it brings the temperature of the water down or a soda really, really quickly. And water is most dense at about 4 degrees Celsius, and the most common form of ice floats, which is very strange. And we can also pollute the water. And how can we pollute the water? Well, pathogens are one. Pathogens are agents that cause disease. So here in Hawaii, for instance, we have leptospirosis and cryptosporidia in our natural water sources, and those are from mongooses and pigs. From their fecal matter, we can get sick from those. Those are examples of pathogens. Oxygen-consuming wastes. So many, fish need to breathe just like we do. Of course, they have gills where we have lungs, but they need oxygen as much as we do. And oxygen-consuming wastes consume oxygen, and that can kill fish. Actually, adding nutrients to water can also be a form of pollution. It can cause something called eutrophication. That causes these dense plant life to form, and that can choke water supplies. Also, suspended solids. These can block sunlight and kill plants, and can clog irrigation ditches and harbors. So I like to swim in Ala Moana Beach Park, and the water is really murky. That water being murky is from the construction going on in Waikiki. So here's an example of eutrophication, and this was prevalent in the continental United States. Phosphate soaps are nutrients, and basically algae grows until it's limited by some nutrient. In the Mississippi River Valley, that nutrient is phosphorus. In the Gulf of Mexico, it's nitrogen. In the northern Pacific Ocean, that's sulfur, and in the southern ocean, that is iron. So if you add any of those nutrients to those areas, you will get eutrophication. And actually that's good because it's bad for us when we do it because it can cause damage to waterways, but that's also where we get a lot of our oxygen. So the sulfur-starved waters around Alaska, when a change in seasons come, there's a churning of water and nutrients come from the bottom of the ocean. And then algal blooms will grow there, and then in those algal blooms will support life. And so, for instance, krill will form, and bait fish will eat the krill, and then certain mammals like the humpback whales will go, and then they will feast on the krill for a very short period of time, build a lot of blubber, and then they'll swim back down to Hawaii, and they'll give birth and raise the calves down here and repeat the cycle. And here's a picture, a NASA picture showing that algal bloom off the coast of Alaska. And this is a seasonal change, and these huge algal blooms generate a lot of oxygen. And algae is the primary source of oxygen for us here on Earth. And like I said, with the migration of the whales, this supports life that way. And pollution, so how can water pollution happen? So dissolved solids, so increasing the salinity of water, the amount of salt water has, that can be harmful for living creatures, fish and plant life. And toxic substances, so what is something that's toxic? Toxic means a substance that causes harm to a normal metabolic process. So that's definition of toxicity. And there are certain types of toxins. We'll talk about a bioaccumulation. That's something that becomes more toxic as it moves up the food chain. Maybe you've heard about that with mercury poisoning. So we'll talk about mercury and bioaccumulation later. So there are many metals. We're not going to cover them all. Let me mention a few briefly. Mercury is mostly harmless, but methylmercury or organic mercury, that's organic means carbon containing, this is very toxic. It's also a neurotoxin. Lead leads to neurological disorders. So remember we talked about that with cars, that cars used to have lead in the gasoline. There was also lead-based paint. So maybe you've heard someone say he or she consumed paint chips when that person was younger. That because ingesting lead to children, especially children, can cause mental retardation. So lead is a neurotoxin as well. Cadmium is also a carcinogen. Cadmium also causes a disease called the ouch disease. Cadmium will replace calcium in your bones and make your bones more brittle, which will make them more prone to breaking. So people that ingest cadmium, besides the cancer, can also get very brittle bones. And there are other metals, and they have various effects, but I just want to briefly mention them. Also mention bioaccumulation. Bioaccumulation can affect us humans. And also some synthetic organic compounds. Some of these are persistent, meaning they stay around for a long time. Some of these are polychlorinated, like hydrocarbons like DDT, dioxin. So Agent Orange, the herbicide used in Vietnam War, had some dioxins in it. So if you ever wonder why it's called Agent Orange, the Viet Cong, they would hide in the jungle. So we decided to get rid of the jungle for them, and we would dump Agent Orange on the jungle. It turned the leaves orange and they fell. It just like falls. So that's why it's called Agent Orange. And also some other PCBs, polychlorinated biphenyls. These can cause thin eggshells in birds of prey. That's from bioaccumulation. It won't affect, so we would put those in various forms, and then bugs would eat them. Certain bugs certain birds like robins would eat the bugs, but then birds of prey like eagles and hawks would eat the robins, and then as it went up the food chain, there would be more concentration at the top, and that caused harm to birds. So that's an example of bioaccumulation. So thermal pollution, this can affect the fish in region. So the problem is that as in general, when you increase temperature, solubility of gases goes down. You know this because cold soda holds on to its carbonation longer than warm soda does, right? So the same thing as oxygen. Warm water will not hold very much oxygen. And maybe you also know this from if you ever did Boy Scouts, or if you boiled water for purification. It tastes kind of flat after you're done boiling it, so if you shake it up for a little bit, then it'll absorb more oxygen, it'll taste better. And when thermal pollution decreases solubility of oxygen, but then it also increases the consumption of oxygen, and it causes a synergistic effect where the oxygen levels go down. And worst case scenario that can happen is if the groundwater gets polluted. And we in Hawaii, at least on Oahu, we more or less drink straight spring water. Other areas, Maui for instance, chlorinates the water, but here in Oahu we're very unique by the fact that we don't purify our water, and we don't chlorinate the water. We drink more or less spring water, but we have a water cycle about 17 years that naturally purifies it for us. Other areas of the country, though, have longer periods of time, on the order of thousands of years, and when their groundwater gets polluted, that's a very tragic thing and can't be safe to drink anymore. And it's also very difficult to clean up. There's not a whole lot one can do once the groundwater is polluted. So how do we purify water? So lime and or alum is added to it as a flocculant, and what a flocculant does, it causes things to float. So a lot of waste will float on the surface of the water. And then typically the water is sand filtered, and then the bacteria in the sand eat the waste, and then we disinfect the water by various methods. Most common here in the United States is chlorination, and then the water is fluorinated. We don't do this in Oahu. We don't purify our water. We drink spring water, and we also do not fluorinate the water here in Hawaii. And this here gives an example of how water purification works. This is not Hawaii, but other places. The water comes in, and then the flocculants are added to get the waste off the surface. And then this area is settling to get rid of any particulate matter. And then this is sand filtered, it's aerated, and to make it taste better. And then chlorine or other things are added to disinfect it, and then sent on to the different homes. And the EPA sets standards for how much water, how much toxins we can have in the water, and here are the standards for the different pollutants that are allowed in water. And besides purifying water, we also have sewage, and there's primary treatment and secondary treatment, and some areas practice tertiary treatment. Most places do not. Primary treatment removes very large objects like sticks and also sludge. So what's sludge? It's human waste and toilet paper, these types of things. And part of the problems going on with Hawaii right now is we only have primary treatment. We do not have secondary treatment. And so we are now arguing with the government about that. And secondary treatment, The bacteria so we have activated sludge eat other wastes, and then these are killed. And the problem with secondary treatment is that there are other nasties that can be formed by it. And then tertiary treatment. The idea of tertiary treatment is to get rid of some of these other things that are that have not been removed in primary secondary treatment. And here shows the treatment. So here is the primary treatment here, that the sewage comes in and then the solids are removed, and then maybe not chlorine is added. This is used for disinfection. And then primary treatment, the wastewater goes from primary treatment to secondary treatment, and then activated sludge comes and gets rid of anything else, something like oxygen-consuming waste. And then this is sent out, and it's also disinfected as well. The reason being is that this activated sludge could also be a pathogen, so it could cause problems for people or to water systems and ultimately humans, because of the diseases that could form from it.